Today we're going to start and finish the notes on nuclear chemistry. Nuclear chemistry, it has to deal with reactions involving the nucleus of an atom. Nuclear reactions are not chemical, although we call it nuclear chemistry, because they don't actually involve electrons per se. They involved particles being emitted or particles being fused to the nucleus of different atoms. So we're going to talk a bit about nuclear chemistry today, and it pretty much has everything to do with radioactivity, and you've probably heard that term before, but radioactivity is when an atom emits particles from its nucleus, and if it does that naturally, all on its own, it's a natural radioactivity. And I know that kind of sounds weird to say natural and radioactive, but there are elements all around you all the time that are emitting radioactive particles or particles from the nucleus of atoms. In fact, you have in you particles that are being emitted all the time. You are radioactive. So radioactivity is emissions from, I'm going to say, unstable nuclei. And a nucleus becomes unstable when the ratio of protons to neutrons gets out of that 1-to-1 ratio. And if you think about it, it kind of makes sense, because in the nucleus of an atom you have all these protons that have this positive charge, and you know what happens when you try to push like charges together. They actually repulse each other, they repel each other, and yet we have this very small dense nucleus that's made out of positive charges. So those positive charges are actually kind of buffered from each other by the neutrons that are also in the nucleus, and they kind of shield that positive repulsion and allow them to exist in that small space. So once you get out of that 1-to-1 ratio, you don't have that nice sweet spot that allows the nucleus to be stable, and instead you end up with these unstable nuclei that would then emit particles from the nucleus. So we're going to use a table today that I referenced at the beginning of the year, Table O. In Table O, you'll see some things that you recognize. You'll see neutron, and the notation for a neutron is a 1 in the upper position, which if you recall, that's where we put the mass in a symbol for an element. A 0 in the lower position here, and that's where we put the atomic number or the charge. So it makes sense that a neutron would have a mass of 1 and a charge of 0. And the symbol we use for it is N. And if you were just going to use a symbol, you can just use the letter N. You'll also recognize here a proton. A proton has a mass of 1 in both of these notations. It also has an atomic number of 1 because it has a charge of +1. And you'll notice here that we can either use an H for hydrogen, because a hydrogen nucleus is actually just a proton. And then you also see there's a P for proton. And if you just used a symbol, you would use P. The other thing you may recognize when you look at the notation is a beta particle. A beta particle, you'll see it has no mass, but it has a -1 charge. And we already know of a particle like that, the electron. And that's what you see here, the E. But we can also use the Greek symbol beta. But if we just use the symbol for beta, we have to use a beta with a negative. And that's because way down here, you can see here's a beta with a positive. It's sort of a strange situation. And if you go into more physics, nuclear physics and stuff, you'll learn more about this stuff. But essentially, the smallest particles in an atom are not protons, electrons, and neutrons. There's smaller things than that. And that's what's being emitted here. So we have a 0 mass, a +1 charge, but we still use the E or the beta, but we want to distinguish it from the -1 charge, so we use beta plus, or we call that a positron. The other types of particles you'll see here are an alpha particle. We talked about alpha particles earlier in the year, but we didn't really say what they were. They have a mass of 4 and an atomic number of 2, which means they have 2 protons, but in order to have a mass of 4, they must also have 2 neutrons, which is essentially a helium nucleus, but we also use the symbol, the Greek symbol alpha for that. So you'll see if we just use the symbol, it's alpha. And then the last thing that I haven't mentioned yet in this chart is gamma radiation. Gamma radiation is just energy. So it doesn't have mass and it doesn't have charge, but we know it's being emitted and we can see the destructive force of gamma radiation. Gamma radiation is very, very small, so it can pass through things pretty easily. Luckily, it doesn't have a huge destructive force, but it can cause some damage. Our skin and our bodies can handle gamma radiation to a certain extent. So they use the Greek letter gamma, which is hard to tell in this symbol, but it's kind of like a Y with a curl on it. Let me draw how I would draw it so you can see. It's like that. So, or an upside down cursive L maybe, but that's gamma. All right. All right. So let's talk about what these radioactive emissions do. And this may seem like common sense, but just to make sure we're all on the same page here, this is a radioactive substance, and let's say it emits many different types of particles. So we have a particle that's being emitted, and you'll see as it passes through our field, this side of our field is going to be positive, and this side of our field is negative. So if this particle on the top side being emitted bends this way, almost toward the positive end, we know it must have a negative charge. Then on the converse down here, we have a particle that bends toward the negative side, so it must have a positive charge. And then this one that goes straight through the field, it has no charge at all. So that's how we started with trying to identify these nuclear emissions. Eventually we got to the point where we could also identify their mass and figured out that some of them were positive and had mass. Some were positive and had no mass. Some were positive and had a different mass than the other ones. Some were negative. Some had no charge at all. So now we use this knowledge to also accelerate particles. In fact, we have a particle accelerator in CERN in Europe. What they're doing there is they're trying to figure out what happens when different particles hit each other. They can actually create some new elements by doing this. Obviously, they're really unstable and don't last long. A lot of this stuff is still being researched. We don't know everything about these things. So let's talk about our different types of emissions. We have alpha particles, and this is essentially just from Table O. In fact, I'm going to shrink that down so we can see that up in the corner here. Alpha emissions have a mass, remember the mass is in the upper left there, of 4. They have a charge of 2, but it's actually a plus 2. The symbol we're going to use for that is alpha. And we're going to get to the stopped by stuff once we talk about all these particles. So you can imagine that an alpha particle is relatively large. It's kind of a big particle compared to all the others. All right, the next one we're going to talk about is beta. A beta particle, when we look at Table O, has no mass. It has a charge of -1. We use the symbol beta minus, and we'll talk about what would stop that particle in a little bit. All right, so you can see I only have 4 emissions that I'm going to go through, and there's actually 6 in this chart. But we're going to keep going here. I'm going to do gamma next. Gamma radiation has no mass and no charge. And we use this funny lowercase gamma symbol for that. All right, we'll do one more. We'll also do neutron. Neutrons, if you look over here, have a mass of 1, but they have a charge of 0. And the symbol we use is just a lowercase n. So really the only other one that is typically emitted is a positron. And a positron is just the same as a beta, except that this would be +1 and we'd put a plus here. The size of the particle is similar, so as we talk about what would stop these things, that would also be similar. So let's say you had alpha particles emitted. Alpha particles, we said, were relatively large particles. It's not going to take much to stop an alpha particle. In fact, you could use just a sheet of paper. A sheet of paper would actually stop an alpha particle. Move that a little bit, and that. A beta particle is much smaller. It has no mass. It does have a little bit of a charge. So this would take a little bit more in order to stop it. In fact, this would probably take a few sheets of aluminum foil. So aluminum foil could actually stop that. Gamma radiation is another thing entirely. It has no mass, it has no charge. It's actually essentially just energy that's emitted from the nucleus, this unstable energy. So you would need quite a bit in order to stop it. In fact, you would need several centimeters of lead. You ever notice when you go to the dentist and they want to take the x-rays, they always put that heavy apron over you? And it's actually got lead in it because that will stop x-ray radiation as well. So lead is really good to protect you from different types of radiation. Now a neutron, being that it actually does have mass, although it has no charge, could actually just be stopped with a sheet of lead. If you've ever been around when mom or dad has opened maybe a bottle of expensive wine or some champagne, sometimes the foil that's actually on that is lead, real heavy, heavier than you expect it to be. So something like that would actually stop it. So now that we have an idea of what some of these radioactive emissions are, we're going to talk about the kinds of things you're going to have to do with that information. So you probably talked about half-life when you took earth science. Half-life is the time required for half of a sample to decay. So we don't talk about half-life all the time, only with things that are radioactive. And sometimes the isotope is radioactive and sometimes it's not. So using that term again, let's go ahead and review that. It's a good time of the year to do that anyway. But this is an element, like different samples of an element, with the same number of protons but a different number of neutrons. All right. So the point in radioactive emissions is that once they've released those particles is that they'll eventually become stable again. That's why they do that. And they'll continue to emit. So if an atom emits a particle and then the resulting element is still unstable, it will emit additional particles. All isotopes above number, including number 84, are radioactive. So you may have noticed earlier in the year, like, Mrs. White isn't talking about those that are above number 84, and that's because they're radioactive. And I don't want you to ever get confused about the difference between chemical and nuclear reactions. You can't change one element into another chemically, but it can happen in a nuclear reaction, which we'll talk about shortly. So half-life, hopefully you've covered this already in earth science, so this will be a quick review for you. So in our question here, we have a 100-gram sample of nitrogen-16, and they want to know how much will remain after 28.8 seconds. So they've given us a lot of information, but we're missing a piece of information that we really need, and that's how long a half-life is. So we have this table N, and how it's set up is that it's alphabetical by the symbol. So we're looking for nitrogen 16, and here it is. And you'll see that its half-life is 7.13 seconds. You'll also notice in this table N, there's a decay mode given. So they've given you the symbol that you can then use to look in table O to figure out the emission. So we'll look at that right now. It's not pertinent to this question, but it actually does beta minus or beta particle right here. So the emission it makes is one of these. All right. So let me set this aside again. So we said it was 7.13 seconds. So the first thing we want to do is figure out how many half-lives have actually elapsed. So we're going to do number of half-lives. This is not actually in your reference tables anywhere. You're going to have to use a little common sense here. So to figure out the number of half-lives, we would take our time elapsed and divide it by the half-life from table N. So in this case, we have 28.8 seconds have elapsed, and the half-life we said was 7.13 seconds. And when you calculate that, you get approximately 4 half-lives. Not 4.5, but 4 half-lives. So that means that we had 4 half-lives elapse. I like to use really concrete math for this. There is actually an equation that you can use, but it has a fractional exponent, and it's really obnoxious. So I think it's a lot easier just to use the box method. So we're starting with 100 grams, and then after 1 half-life, so if 1 half-life elapsed, we'll have half of that, or 50 grams. After a second half-life, we'll have half of that, or 25 grams. We need to get to this 4, so we'll keep going. After a third half-life, we will have 12.5 grams, so we keep dividing it in half. So after a fourth half-life, we would have half of that, or 6.25 grams. And that is actually our answer. That's how much we'll have left. So let's try this in a little different way. So we have 2.50 grams of strontium-90, and it remains unchanged after 116.4 years. They want to know what the original mass was. So we have what we got at the end of all the half-life periods to be 2.5 grams. So we're going to have to work backwards to figure this out. There's no one way to do this, but I'm going to show you the way I would do it. I'm going to figure out how many half-lives have elapsed, and that's going to help me work backwards. You could look up in the table exactly what the half-life is and then use that in a different way. I'm not going to do that this time, but you could actually add up the years. So here we have our table N, and we're looking for strontium-90. So it's alphabetical by symbol. Here it is, 29.1 years. So you could actually, although I won't do it this way, you could actually be filling in the years here instead of the half-lives above the arrow. I'm not going to do that. I'm going to take my 116.4 years, that's my time elapsed, and divide it by my 29.1 years, which is my half-life, so I can figure out how many half-lives have elapsed. So my math here, 116.4 divided by 29.1, and we get 4. So 4 half-lives have elapsed. So this is how much we had left after 4. Prior to the 4, we would have had twice that, or 5 grams. So that would have been after 3 half-lives. Before that, we would have had twice that, or 10 grams. So that would have been at the end of 2 half-lives. If we double that, we would have what we had after 1 half-life. But this is where it gets tricky. This is after 1 half-life. We want to know what we had prior to that, and that is 40 grams. So this is my answer. This is what I started with. So what I was talking about with the years, you could, knowing that it's 29.1 years, you could do 29.1 and then add 29.1, and you would get, what is that, 58.2? I don't know if I did that in my head. And then keep going until you got to your 116.4 years. So actually, I know I need twice that to get there. So here's your 116.4. I don't do it that way. I like to do the math to start with. All right. Something else we need to do with this is a transmutation reaction. A transmutation reaction is when one element decays into another. And it does that by emitting particles from the nucleus. What makes it natural is that it does it all on its own. It's naturally radioactive to start with. You can tell you have a natural transmutation reaction because there's only one thing on the reactant side. You'll see in a few minutes when we talk about artificial that there'll be something additional here. It has to be hit with a particle in order to make it radioactive and make it emit a particle. In a natural transmutation, you're only going to see that one reactant. So let me show you what we're going to do. When you have a natural transmutation, it's going to be one from this table, or they would have to give you more information. So we're going to be looking up in Table N what the decay mode is going to be for that element. So we have uranium-238, and you need to make sure you know which one because there's 3 of them here. Uranium-238, when it decays, it emits an alpha particle. So what I like to do, I like to put that over the symbol, or the arrow. I put the symbol over the arrow, and I'm going to do that for the other ones too. It's going to save me a little flipping back and forth. Nitrogen-16 is beta minus. Phosphorus-32 is beta minus. And then iron-53 is beta plus. Now, if you have your reference tables, you'll see this is on one page, and then table O is on a different page, which can be kind of irritating. So that's why I looked everything up to start with. So now I'm going to use table O in order to figure out the notation. The notation for each of these is what's going to go in this spot here. So for alpha, you have a choice. You can either use the 4/2 He or the 4/2 alpha. Either way is entirely correct. Really what's important are the numbers. Okay, for the beta minus, it's 0 and -1. And I like the beta sometimes and the E other times. Same thing for the phosphorus. All I'm doing is pulling these from table O, and then beta positive is 0 plus 1 beta. So for the most part, what you're going to be doing now, and for all of these this is true, you're going to be figuring out what this other thing is, this missing piece is, based on the fact that your top number from the left side has to be the same total on the right side. So if my uranium has a mass of 238, I need to conserve that on the right side. So since I've already said this is 4, then the mass of whatever I'm figuring out here must be 234, because now the 2 of them added up will be 238, just like here. And we're going to do the same thing at the bottom. We have 92. Since alpha has a charge of 2, then this must be 90. All right. Now we need to figure out what the symbol is for this new element that this transmutated into. And all you're going to do is look in the periodic table. So there's a lot of flipping around here. We'll get out our periodic table, and we need to find element 90. Element 90, so here is our periodic table, and element 90 is here in my lactanides. I think that's how you say it, lactanides. Here is TH. So I'm going to get this out of the way. We'll need it again in a minute. TH. This being above number 84 is also going to decay at some point, but we're going to leave that alone right now. All right, let's try the next one. We have a total mass on this side of 16. Since this is 0, our new element will still be 16. In the bottom here, our total charge needs to be 7. This is -1. So in order for this side to total 7, this would have to be 8. So it's actually a higher number. So we're going to look in our periodic table, find what element 8 is. Here it is. It's oxygen. So this is actually turned into oxygen. And it's actually a 1-to-1 ratio. It's no longer going to be radioactive. All right, let's look at our next one.